Now, the Doppler effect is an interesting wave phenomenon. One way to try to understand the Doppler effect is to imagine that we're looking at the surface of a lake with bugs going across the surface. And as these bugs are, using surface tension to stay on top of the water, their legs create little wavelets that move out. Every time I see a video like this, I think that there's going to be a bass coming up there to grab one of those bugs. As these bugs go across the surface and create these waves, I better pause that video over there. As the bug goes across the surface and creates the waves, we can represent the wave crest as these blue circles. And so the distance between the blue circles is the wavelength. So crest to crest is the wavelength. Now, if this bug begins to move as it's creating these waves, when it was back here at position 1, it created this wave that propagated outward to this point, and then at position 2 here, position 3, and then position 4. What you begin to notice is that if the bug moves toward the right, you'll notice that an observer at point B will notice that the wavelength is shorter as the bug approaches the observer. But if the observer is over here behind an object moving away, then the wavelength is longer. Now this is, kind of a simple example dealing with water waves, but this is how the Doppler effect works also for sound and light as well. So here's an animation that demonstrates this. An object that is at rest, whether it's creating water waves, sound waves, or light waves, our observers in all directions will see the same wavelength. But once you begin to put that object in motion, in this case going over to the right, you'll notice that an observer over here sees a short wavelength, and an observer over here sees a long wavelength. That is the definition of the Doppler effect. The Doppler effect is the change in the wavelength of the wave due to motion of the source. The source could be something creating a disturbance in water, creating a sound such as a buzzer or a horn or something like that, or an object that's giving off light in the case of a star or, well, any light source really. So one example or one kind of other definition we could use for the Doppler effect is this right here. Kind of a silly definition. If we have an observer in the middle of this figure here, noticing a fire truck coming toward them, you'll notice that the wavelengths here are short, creating a higher pitch wee sound, and as the fire truck drives away, the wavelengths are longer, so it kind of makes an ooh sound. I wonder if I have an audio of this. Wait, I think I do. Okay, well that's not a fire, it's obviously not a fire truck sound. That's a horn from a car. And so you'll notice two things happen when I play it again. One of them is the volume gets louder and then softer, but that's not the phenomenon that we're talking about for the Doppler effect. We're talking about a high-pitched sound as it approaches and a low-pitched sound as it goes away. Here it goes. So you notice the pitch changed as the object moves. Whoa, it's a little too loud on that one. So an example that we can use for the Doppler effect are moving cars that are making noises. And another example we've often heard of is Doppler forecast or Doppler radar used for weather. The Doppler effect allows you to determine whether an object is coming toward or away from you. You can use that to determine whether clouds are coming toward or away from the Doppler radar detector. That's how we know what the wind speeds are in many cases for storms and hurricanes. The Doppler effect is also used in police radar for determining speeds of vehicles. It's also used for air traffic control as well, for determining speed in some cases. Whoops, how did I get back to the bugs again? Let me pause that. Sorry about that. All right, here we go. Where was I at? All right, now I want to talk about police radar a little bit. So suppose you have this car coming in from the left-hand side. I'll have it come in there. And it's moving with a velocity, let's say, toward the right-hand side. Now the true velocity is going to be represented by this arrow that looks like that right there. Suppose that you have a police officer off to the side of the road. Now the police officer could be, directly in front of and have this radar gun that's pointing in this direction. The radar gun that I'm talking about emits radio waves out of it, and then it bounces off the curved edges of the car and then bounces back. So it emits a certain wavelength of radio waves at your car, and then the wavelength gets changed when it returns because of the motion of your car. So the change in wavelength due to motion of the source. That's what the Doppler effect is. That's how it's used for police radar. So the radar gun not only transmits a signal out, but it also detects. It looks at the difference in wavelength and is able to get your speed. One of the things that you should know about police radar, perhaps, is that you're only going to get a component of the actual speed. For example, if you were going 70 miles an hour for your true velocity straight forward, police radar will always read something less than what you're actually going. It will always be a component. So to be effective with radar guns, you kind of have to be almost in front of it to get the true velocity. And so this position right here, off the side of the road, maybe at this 30 or 40 degree angle, the driver might be going 70 miles an hour, but they might only read 60 at this position. And certainly if the radar was over here, if the radar gun was this direction, it shined radio waves out and then it came back, it's going to get zero velocity because the Doppler effect only works for objects that are moving toward or away from the observer. So just to summarize here, police radar detectors always measure something less than what you're actually going. Well, maybe equal to or less. All right, so the Doppler effect also applies to light. In that last example, we were talking about radio waves and radar. Radar stands for radio direction and ranging. Radio waves is a form of light. What happens is you get a change in wavelength that also corresponds to a change in the light frequency. So as you have an object that approaches you, the frequency gets higher for light, just like the pitch got higher in the case of the car horn. And similarly, if an object is moving away from you, then you get a decrease in the frequency of light, just like you got a decrease in the pitch of the sound from the horn. One example that is used, especially in astronomy, is that if you have a star spinning, you can actually look at one side of it and see it approach you, and another side is spinning away from you, and you can use the Doppler effect to measure the rotational speed of a star. You can also determine whether the star is coming toward the Earth or a star is moving away from the Earth. I found this figure online and I noticed this nice Doppler effect diagram, so I wanted to show you what it looks like. So if stars are coming toward you, you'll see a shorter wavelength, which corresponds to a higher frequency, which corresponds to bluer light, which is why it's called blue shift. And if a star is moving away from you, the Earth that is, then the wavelength is longer, the frequency is lower, and if the object is red, well, it has a redshifted spectrum. So to put it short and simple, instead of the very lot of text on this slide, I wanted to make it a lot simpler. Simply put, in chapter 19, we see that blue shift is the increase in light frequency, bluer light, toward the blue end of the spectrum, and then red shift corresponds to light frequencies toward the red end of the spectrum. Someone told me they had a mnemonic for remembering the difference between these two. They said that if you have a star that is blue shifted, it's like a person walking toward you and you can see their blue eyes. And if you have a star that's red shifted, it's like a car driving away from you and you can see their red taillights. Now, obviously, that's just a mnemonic, toward blue eyes, away red taillights. It just kind of helps you remember the difference between the red shift and blue shifted spectra.